Okay, so we continue. But before that, Brian, the last part, which one that you are referring to? Can you, perhaps I can explain again. Slide 23. This one here, the cross product. Regarding the cross product, no. Oh, this one here. Sorry. Mm, okay, the surfaces. All right. Um, maybe I will try to draw again. So I'll try to draw again. Okay. Okay. So let's see the unit vector now. So the unit vector will be in this way. Um, so let's say this is the point. Okay, this is the point here. So the unit vector is d rho. Okay, and then here's dz. This is a unit. Sorry, what I'm doing. Rho cap. Sorry, rho cap, z cap, and phi cap. So I'm just drawing this as your reference coordinates, unit vector coordinates. So we have knew that this length here, is rho d phi. Yes, and this length here is dz, and this length here is d phi. Okay, d phi. Okay, so even though it's curvy, I mean, it's supposed to be curvilinear, but because of the small differential displacement, so the small differential displacement, so we assume that, so I will mark it with red for the length, same length here, 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 and here is the same. Okay, and here, 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 and here is the same. While here, 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 and here is the same length. Okay, so the rationale here is, it's supposed to be some kind of length, different length here, because of this a small displacement, a very small displacement. We will assume that the one that I mark with the same color. So this differential cubed. So the length is the same, the one that I mark with the color. So that means the red ones are rho d phi, the curvy length, and the green one are dz, and the blue ones are d rho. So coming back to the surface direction, So for example, I'm talking about this surface here. So the red surface, let's say, I say the surface S is, so it should be d rho d phi multiply dz. Yeah. So if you look at this surface, the vector perpendicular to this surface is phi cap, right? So as I give a reference point here, so the vector perpendicular is phi cap to the surface, to this surface here. So what about this surface? Maybe I will use this surface, maybe. I will remove this, okay? So let's say this surface now, this top surface. So it should be rho d phi, so which is this length. So I will use a different color now, okay? Maybe, yep. So rho d phi multiply with this length, right? D phi. So the vector which is perpendicular to this surface, the vector which is perpendicular to this surface is z cap, right? Do you get what I mean, everyone? What about the rest? I mean, is this okay? All right. Okay. So let's move on to the next spherical coordinates. So for spherical coordinates, we have one length dimension and the other two represent angle. So r theta d phi. So where is r? R is referred, let's say I have a point here, and this P point, this point P here, this point P here, okay, I can represent as, is the same as XYZ, and also I can represent as theta, r theta phi, okay. So there will be a relation between r and XYZ, theta with XYZ, and phi with XYZ. So what is phi here? So phi, the direction of phi, or is the same as the cylindrical coordinates, while theta, the theta measure is from the z-axis, okay, from the z-axis to the z-axis measured. So it is projecting down to the negative z-axis. Okay, it's projecting down to the negative z-axis. Okay. So the limits, the limits of r, the limits of r, the radius, for the radius for spherical is range from 0 to infinity. Theta is 0, so measured from the top axis z down to the negative z axis, which is 90 degrees. So which is 90 degrees here. And phi is the same as the cylindrical one, which is 0 to 2 pi. So that is the range for phi. So, and of course, the unit vector are r cap, phi cap, and theta cap, theta cap and phi cap. So that is the unit vector. So if a point A is expressed in terms of cylindrical components, so which corresponds to AR, A theta, and A phi. So the magnitude of vector A, same as how we do it in Cartesian. So it is square root of each of the component, AR squared, A theta squared, A phi squared, A phi squared, yeah. And the dot product between the same component is always 1, and the perpendicular vector is always 0. So the unit vector, so let's say this is my xyz. So if I'm going to, so let's say now this is my x cap here. So I now I represent this as the unit vector. So for this, I will also represent this as unit vector. Sorry. So this direction here is r cap, okay, and the phi cap will be in this direction. So we have to use a little bit of imagination here. So this is phi cap, okay, and also theta cap. So how is it that this direction theta cap is pointing down, is pointing in this direction? Because if we go back to let's say this diagram here. So if let's say if this is your point here, if let's say we are moving at a constant length r, if let's say this point is moving to this point here, okay, so here to here, it is pointing in the theta direction, okay. So therefore the direction, it seems that it going down, okay. So this is theta cap direction, okay. So if I bring back, if I trace back to the origin, so if I put this at the origin, it will become like this, come like this. And for the phi cap, so bear in mind the phi cap lies on the x and y axis, sorry, x and y plane, yeah. The phi cap is lies on the x and y plane, okay. So again, the unit vector for r cap, phi cap, and theta cap, they are all 90 degrees perpendicular. They are orthogonal with each other. So therefore, the dot product between r cap and r cap is always 1, and between the perpendicular unit vector is always 0. So I don't have to explain this again. You can um, use your right hand rule to determine the cross product between r component with the theta component. So r component crosses theta component. So unit unit vector r component crosses with theta component, produces phi. Yeah. Then theta component crosses with phi component, produces r, and phi component crosses with r component, produces theta. Okay. So how the relationship between xyz and the and the spherical coordinates is such that r is equals to x square y square plus z square, right? This is r. Yeah, this is r, this point here. And theta, so if I know r, okay, so theta is, let's say this is the point z, right? So this point here is z. So this length here to this length is z. And I can find this length. Sorry, maybe I use a different slides. Okay. All right. So this length here is rho. Yeah. This length here is rho. Okay. Um, I will mark it with a color red. All right. This length here is rho. Okay. Rho is actually square root of x squared plus y squared. Okay, so if you look at the projection from here, let's say this is much easier to see. So as we know, point P is x, y, z, and therefore this length here and this length here is the same, right? So they are parallel lengths. This length and this length are parallel. I mean, this line and this line is parallel, and therefore the length is the same. In this case, if you look carefully at this, and theta, how we define theta? So this point here is z. This point here is z. So theta is equals to what? What is theta? So I have two variable here, and this is a triangle, right angle triangle, right? So what is this? Theta is equals to? Anyone can tell me? You can type in the chat box. So theta is what? No one? So according to this diagram here, according to this diagram, so I have provided you the length z, okay, and also rho, right? So let's say we define that this length here is rho. So as I mentioned, this triangle is right angle. So what is theta? To be expressed in terms of z and rho. Yes, correct. Arctangent rho over z. Yes. Rho over z, which is arctangent square root of x squared plus y squared over z. Okay. All right. So so phi is the same as what we have defined earlier. What we have defined earlier for cylindrical. So phi is actually arctangent of y over x. Yeah. So this is what we have, and this is the relation of how we find. Let's say you are given x, y, z. Let's say we are given a coordinates of x, y, z, and how are we going to transform to spherical coordinates by using this formula. So similarly, if let's say we are given um, spherical coordinates and translate back to Cartesian x, y, z. So same. Um, if let's say we are given r, theta, and phi, so the x, so the z coordinates is the projection of this. So it's the z is the projection of this vector here, the projection of this vector onto onto the z-axis. So if let's say I'm given r and theta, projection of this length onto z-axis, so which is r cos theta. Okay, and then the projection of this length onto the xy plane, projection of this length onto the xy plane. So this length here now is rho, which is rho is r sine theta. Okay, r sine theta. And again, I will project rho onto x-axis. So therefore, x is, so given that this is phi, if given this is phi, so given that this is phi, so the x is just the projection of this length, the length rho onto x, which is rho cos theta. So which is, I can write this as r sine theta cos theta. Okay, sorry, cos phi, sorry, cos phi, sorry. So same goes for y. So it's a projection of this length to the y. So it will be sine y. Sorry, sine phi, sorry. R sine theta sine phi. So the differential length now. Um, so this, okay, again, I'm going to start with a point, and then from the initial point, we'll move across the, let's say, from here, from this red dot here to here, let's say, to the green point. Okay, from one vertices to another vertices. So a small differential displacement. So first, um, moving here to here, let's say. So from red dot to the black dot, it is dr. Okay, so the differential displacement is dr in the r direction. Okay, dr in the r direction, r cap. Then from the black dot to the blue dot, so this displacement now, it is basically from here to here, it is r sine theta d phi. Okay, and to here is theta. Okay, so this point here will be theta, r theta, sorry. So this point here will be r theta. Sorry, not the point. I'm talking about the arc length here, r theta. Okay. So traces from here to here. So that's the differential length, okay, dl. So in this is the theta direction, and this will be the phi direction. And then the volume is just we multiply these three components. This component here, this component and dr component. So that is the differential volume. Okay. So there is a few transformation that previously that I talked about, but I just provide um, the formula now to you. So there's a few transformation between how we transform x coordinates to y coordinates for the unit vectors, and from there, from the unit vectors, then we can obtain the scalar vector component. So of course, if you are given a point of x, y, z, so that point we can always translate into coordinates. So I'm talking about the direction of unit vectors. So how are we going to transform from one um, coordinate vector system to another coordinate vector system? We haven't talked about it, but I will just briefly go through with you how this unit vector transformation comes about. And basically, it's just the application of dot product, as simple as that. And eventually, we can find from the unit. Once we can find what is the unit vector, we can also find what is the vector component, the associated vector component. So I'm going to show you between Cartesian and cylindrical. That means how are we going to transform between Cartesian to cylindrical and cylindrical back to Cartesian. So unit vectors. Okay. So I'm just going to show you one, and I will leave it to you how you want to do it for Cartesian to spherical and spherical back to Cartesian, and also between Cartesian to cylindrical to spherical, and spherical back to cylindrical. How are we going to do that? So it is the same. The method that I'm going to show is applicable to how we can obtain the vector transformation, the vector coordinates transformation. Okay. So I'm going to write down only, because since x, y, z for cylindrical, sorry, for uh, Cartesian, from Cartesian, let's say we have a point x, y, z, or x cap, y cap, and z cap for the unit vectors. Okay. And for cylindrical, so the unit vector is say r cap, phi cap, and z cap. So the z cap and z cap is the same, so I do not have to worry about the transformation here. So I will find the transformation of vectors for between r cap and phi cap and x cap and y cap. So first, I will draw the unit vector direction for x and y. Okay, so now you try to imagine now that you are looking down from this direction. Okay, the arrow. So imagine that this that you are looking down from this direction. So now your point of view should be like this. So I will replace this as unit vectors. Yeah, unit vectors. For cylindrical, we have a radial direction, which is r cap. Suppose you have a point here, okay? This is direction of r cap. And then, as I said, if let's say from this point, I move to another point here. So this is perpendicular. If let's say I want to associate a vector to this direction of motion. So let's say the same radial length, and let's say the motion, make a small angle d phi. Yeah, just assume that for now. So if I want to associate the direction of motion from this point to this point, so this is the unit vector, which is tangential to this curve, here. So rather than I draw it from starting from this point, so I'm going to bring this vector here. I'm going to bring this vector here to here. So this is r cap. So the r cap and phi cap is perpendicular, while x cap and y cap is perpendicular. Okay. And this angle here now is theta. So bear in mind so maybe I remove the 90 degrees angle. So I will remove. So it's a bit messy. So bear in mind the r cap, the unit vector r and the unit vector phi is perpendicular. Unit vector x and unit vector y is also perpendicular. And this make an angle of theta. Phi, sorry. Phi, sorry. All right. So think about what I have mentioned just now about dot product. I said is quite important, and we are going to see this application when when we're going to translate, if let's say given the unit vector direction of x cap and y cap. So I'm going to translate into vector coordinates for cylindrical. So now I have a chance to show the application of this. So this is phi as well. Yep. So bear in mind, because it's 90 degrees, right? So this 90 degree, this is 90 minus theta, and this is 90 degrees. So therefore, this is phi. Okay, now. If let's say x and y is given, so we know the unit vector direction x and y, and as we know that the cylindrical has a radial component pointing in this direction, and we know that we have a phi angle made between them. So I can represent this as r cap. So it's x cap cos phi. So it's a projection of x unit vector. It's the projection of x unit vector to r unit vector. However, there is also a contribution. There's a contribution from there's a contribution from y unit vector, right? So I can write this as y cap cos 90 minus phi. So we knew that cos 90 degrees is what? Cos 90 cos phi plus sine 90 sine phi, right? So here I expand using the compound angle. So I hope you still remember what is cos A minus B, cos A plus B. So I've expanded this as cos 90 degrees cos phi. So cos 90 degrees is 0. And sine 90 degrees is 1. So therefore, this is x cap cos phi plus y cap sine phi. Okay. And what about theta component, phi component in the phi component direction? So what about that? So now, if let's say I take the projection, so I'm going to project x to phi direction. Okay. So for phi cap, so I'm going to say this. So here, I'm going to project my y to phi cap. So it's going to be y cos phi. Okay. I'm going to project the unit vector y to cos phi. And then plus the contribution from the x unit vector. So x unit vector cos. So this is 90 degrees. So 90 degrees minus plus phi, sorry, right? So here to here is 90 degrees plus phi. So this is the angle of projection. So again, this is cos 90 plus phi. So cos A plus B. So it should be minus sine phi. Okay. So if we, so I'm going, so if we look back at the formula given, so now you can see now. So x cos phi plus y sine phi, okay, which is given here, which I have just explained how is obtained. So y phi phi cap is sorry, negative x sine phi plus y cap cos phi, which is here. Okay. And again, I mentioned just now that because there's no the z direction is the same for Cartesian and cylindrical, so there's no changes, there's no transformation needed, and therefore the associate vector component can be easily obtained now. So based on this unit vector transformation, okay, from x to y, so I can rewrite this as a matrix. And rewrite this as a matrix here. So let me rewrite that again. I will rewrite this again. X cap cos phi plus y cap sine phi, and phi cap is negative x sine phi. Okay, so I can write this now in terms of matrix. Yeah. So I can write this as matrix. So I've translated this into a matrix, a transformation matrix between um, cylindrical coordinates and Cartesian coordinates. So if I mean you so far I've explained the application, how we can obtain all this transformation using dot product. And same goes for, if let's say you can also you can also derive the formula from cylindrical to Cartesian. Yeah. So this is the transformation matrix from Cartesian to cylindrical unit vector. So I will just I will just stop here. I won't go all the way, but so the remaining part, if let's say you want to understand more and you want to get the feel of it, of how this formulation works, so what I will advise you is try to derive the equations between Cartesian and cylindrical, cylindrical and Cartesian, and subsequently there's also between Cartesian and spherical, spherical and Cartesian. Try to obtain it on your own. Okay. As I said, it's a good exercise for you. You'll be given this transformation formula, so in the exam, so not to worry. But it will be a good exercise for you, algebra, for algebra exercise. So this is my explanation for for our revision, for the mathematics fundamentals revision. So this up to here. Okay. So before we end, um, is it is there any questions that you would like to ask? So please let me know if at any point that you do not understand, I mean, where I've explained. Do you understand the transformations that, I mean, the formulas that I'm trying to show you? How is it obtained? Do you understand this part here? From Cartesian to cylindrical. Okay. So far, two have replied me. Okay. All right. So I think we have a long day. Okay, we have a long day for today because we have one tutorial session and we have continued so far, and I think it's better for us to stop at this point. Okay, so because we are going to meet tomorrow again, so I will continue the lecture session. So the revision for the mathematics. So I will stop here. Yeah. So this is what you should have required. I mean, you should have know before we embark further the course in electromagnetics. So far this is what you should know so far, and the subsequent and then the subsequent uh, theorem. So we will encounter a few theorem later on. So the subsequent theorem I will explain to you further once we encounter that. So once we want to apply that theorem, so I will explain to you again some of the physical understanding that associate with it. So I will explain again. So not to worry. So far for the maths, this should be enough for now. Um, so there are some exercises I given out for the maths. So I hope you should try that um, at your own time. Please try it. Okay. Please refresh some of the um, mathematics that include vector algebra and also vector calculus. So I haven't go through the vector calculus yet. So as I said, as we go as we go along, so we will encounter this. Uh, we will encounter the application of vector calculus, some part of it, and the recurrence of vector calculus for both electric field and magnetic field. So I will explain again what is the physical significance, what is the physical meaning of that in a later stage. All right. So I will before we end our session, please um, remember what I said. If you do not understand certain things, please let me know. Set a time. Um, I won't be hesitate to. I won't be hesitate to uh, attempt to your questions. So uh, please do not hesitate to contact me. So a lot of students who didn't do well in this course just simply because um, at some point when they feel they don't understand and they leave it at one side and then they don't try um, to understand by attempt the questions. So I won't scold you, all right, because you want to learn. If you want to learn, I will teach. All right, that's my advice to you. So please set an appointment. So at any point, at any part of my explanation so far, if you do not understand and you want to clarify, please set an appointment with me. Or before the start of the classes, before the start of next classes, for example, you want to clarify something, we can have a discussion together with the class. So I hope you take this advice. All right. Basically that's all from me for today. If you want to ask me something, please ask me now. How to do it in reverse? Okay. um so if let's say you want to do it reverse, you have two methods here. One is, so as I have presented here, using a matrix. So you can do an inverse matrix for this, for example. So you can do an inverse matrix. So for example, now I can do a inverse. So the reverse of this, you can do a inverse matrix of this. Yeah. Sorry, I forgot to share screen. Sorry. Yep. So you can do an inverse matrix. So as I said just now, I have presented to you the matrix representation. So you can do an inverse matrix of this. For example, this is the inverse matrix. Okay, so this is one way. So you still get back, I mean, you still get the answer by inverse matrix. Another way is, again, we can apply. So we can apply this here. So I'm going to copy this. Okay, so now assuming that given given the unit vector r and phi, yeah, the unit vector r and phi. So the rest of the dimension is the same for phi. Okay, and now we want to find x. Yeah, so I want to find x cap. I want to find x cap. So there are two vectors that contribute to the direct, I mean, uh, to x cap, which is the unit vector r and phi, right? So I'm going to project my r to phi. So again, the projection is r cap cos theta, sorry, cos phi. So projecting r to x and projecting phi to x now. So phi cos um, 90 plus phi, right? So this is simply r cap cos phi minus phi cap sine phi. Okay. So what about y? Y cap. So projecting r cap to y and projecting phi cap to y direction, y cap direction. So this is r cap sine phi plus phi cap cos phi. So this is how you will get it. So it's the same. It's reversible. So when we want to get Cartesian to cylindrical, sorry, Cartesian to cylindrical or cylindrical to Cartesian, so we just apply the dot product. So how we are projecting the unit vector to the other unit vector direction of interest. So I've demonstrated here. So I'm going to represent this in vector form. So r cap. So I will rewrite this here. Sorry, not r cap, x cap. So again, we can represent this in matrix form. Cos phi minus sine phi 0. Then we have sine phi cos phi 0, 0, 0, 1. So this is r cap, phi cap, z cap. So if you can try to compare your answer by doing the inverse, by doing this inverse here. You can compare the answer by doing this inverse here. Okay. Um, okay. And then compare your answer to this. So you should get the same matrix here. So it should be the same, yeah. So x cap is minus, yeah, correct. Right. So Muhammad Adin, so you get my explanation? All right. So we will stop here for today. We will continue tomorrow again. So we meet again in afternoon. So I will proceed with the core of the chapter. So we will proceed to chapter 1 tomorrow. Okay, everyone. Um, thank you, everyone. Thank you for your attention.